Thanks. I'll start. Dear Heavenly Father, we thank you for this day. I thank you for these students, and I just ask that you just guide our work today, Lord. In your name I pray. Amen. So, today I need to talk to you guys about integration. So, complex integration. And I will admit, I'm not, well, let me just get to it here. So my chapter 8 has a lot of things from Gamelin. I'm going to try just to hit the high points here. So, you know what? No. I'm going to chapter 9. Going to chapter 9 here. I debate. I'm a victim of my own indecision here. I'll stick with chapter 8. Definition. Let f and g be real-valued functions on C, which of course we can think of as R2, then we can define a few things. One of the things we can define is the integral of f plus ig dA. And really a double integral, all right? So the double integral of a complex valued function over an area, we're just going to define that to be the integral of the real part plus I times the integral of the other part, the imaginary part, yeah? And so this basically just says that if you want to integrate a complex valued function over an area, integrate the real part, integrate the imaginary part, that's it. Right? It's very, very natural definition. Another thing I should mention, I think we've already talked about this, but if we're going to partial differentiate, how do we partial differentiate a complex sum of real valued functions? We just take partial derivatives. I mean, this has been introduced in this course already, but just a reminder, this is how we partial differentiate with respect to a real variable, a complex valued function. And we can also do things like the integral over a curve of, say, f plus ig dx. That is going to be the integral over the curve of f dx plus I integral of g dx over the curve. And likewise, if you don't mind, we could do the same thing with y, right? We define integral with respect to dy in the same way. These, we talked about we defined how to calculate these kind of line integrals back in Calculus 3, right? You find a parameterization for C, and you do the integration, right? So we could just as well do this for y, all right? And then, of course, we could also do something like, we could define the integral of, let's see here, how to say it. Well, p dx plus q dy to be equal to the integral of c of p dx plus the integral over c of q dy, where p and q are complex valued. So like p is equal to p1 plus I p2, and q is equal to q1 plus I q2. These kinds of integrals we could also define. And here I'm using this to define that. Right? So what I'm trying to tell you at the moment is just we can do everything we were doing in Calculus 3, essentially just replacing real valued functions with complex valued functions. And pretty much everything just goes through the same way it did before. All right? Let's look at a non-trivial not a non-trivial application of this idea. We can prove Green's theorem over a simply connected region for something like the last thing I wrote. All right, so there's a theorem. What's Green's theorem say? It says the integral of p dx plus q dy over the boundary of some region, right, positively oriented boundary, is equal to the what? The integral of partial q partial x minus partial p partial y, yeah? The double integral over the region, right, dA? This is Green's theorem, yes? Now, of course, in Calculus 3, we prove this for what? For real valued functions p and q. What I'd like to explain to you is that this is equally true if we look at p and q being complex valued. All right, so what's the proof? So, all right. So we're going to say p is equal to p1 plus ip2, and q is equal to q1 plus iq2, right? And so if I integrate over the boundary of the simply connected region, R, p dx plus q dy, by definition, that is p1 plus ip2 dx plus q1 plus iq2 dy. And then by the definition of such integrals, we can break it up into a sum of two real integrals, one of them multiplied by I. See, the definition is, so this, using my definitions that I think are written annoyingly carefully in the notes, so annoyingly carefully that if I actually wrote those things out in class, we'd be here. That would be all we did the rest of the semester, I think. I mean, I don't know. So p dx plus q1 dy plus I times the integral of p2 dx plus q2 dy. My point is you can break it up into the real part and the imaginary part like that. All right? And then what we can do is we can apply Green's theorem separately to both of those line integrals, which are just plain old real line integrals. Right? This is the work done by what? If you want to go back to that. Work done by P1, Q1 along the boundary of R, right? And likewise, this would be the work done by what? P2, Q2, right? P2, Q2 along the boundary of R. So this one complex line integral is saying something about two ordinary line integrals, right? A single complex vector field has two real vector fields hiding inside it, if you look at it like this, the real part and the imaginary part. Fine. The point, though, is we can apply Green's theorem to both of these separately, yeah? So Green's theorem to the first piece gives me double integral over R of partial q1 partial x minus partial p1 partial y dA. And then we got plus I times the integral over the region of partial q2 partial x minus partial p2 partial y dA. All right? But then by the definition of a complex valued double integral, that's exactly what? You can combine these, yeah? So we've got partial x of q1 plus iq2 minus partial y of p1 plus ip2, rearranging terms, yeah? And using the definition of partial differentiation of a complex valued function, which is just that we partial differentiate the real part, partial differentiate the imaginary part one at a time. That's, yeah. I don't know if well, anyway, this is exactly what partial q, partial x minus partial p, partial y. So good news, folks, Green's theorem still true if we let P and Q be complex valued. The natural definitions make it so. All right? Any questions about this so far? So what I'm doing in about the next, hopefully just 10 minutes of class, is just reiterating things we should know from Calculus 3 about vector fields and integrals along curves and things. It turns out all of those results have natural analogies for the complex valued analogs of things we learned in Calculus 3. I started with Green's theorem, but next up we can talk about exact and closed forms. So if, well, first of all, just terminology. We say omega equal to p dx plus q dy, where p and q are complex valued. This is a, well, it's a differential one form, all right? Or you could say it's a differential form. Complex valued differential form. Complex valued differential form. Right? Now you can talk about complex valued differential forms and you can decide whether or not they're exact or whether or not they're closed. What does it mean for it to be exact? I guess I should mention a definition. dH, all right, is partial h partial x dx plus partial h partial y dy. You're like, well, that's not new. I knew that from Calculus 3. That's just the total differential, right? So here I'm thinking of h as being a function. But here's the rub. In Calculus 3, h was a function from, say, R2 to R. It was real valued. Now I want to think about h being complex valued. So here we're thinking about h being a function from c to c. All right? It's a complex valued function, and we just took the differential of it, and it gave us a differential one form. All right? This is something we can do. That's how you define it. Now, definition, omega equals p dx plus q dy is exact on U, which is a subset of the complex plane, if there exists h, which is a function from U to C, such that dh is equal to omega. All right. This is what it means for a differential form to be exact. You can write it as a total differential of some function. All right. Exactness is something that comes paired with the concept of a domain. I don't just talk about a form being exact. If I do, I'm being sloppy. We should talk about exactness with respect to some domain of consideration. Yeah? So otherwise, by default, the domain is taken to be as big as it possibly can be, right? So there's a natural domain once you write down a formula, right? You just take it to be the set of all z for which the formula makes sense. That's our custom, right? So if I don't say u, it's understood that the domain should be the natural domain of the expression, which is just as greedy as possible, right? So that's an exact form. Then there's also a closed form. Omega is closed if partial q, partial x, minus partial p, partial y is equal to 0. Or you could just say that those are equal. This is the closed condition. All right? You could guess why I wrote it the way I did rather than equality. All right? So This is exact, this is closed. All right. One of the theorems we can prove easily and immediately is that exact implies closed. All right. Exact implies closed for a differential form. How is that? Well, if we have omega is equal to partial h partial x dx plus partial h partial y dy, right? Then this is my p, this is my q. So partial q partial x is equal to, partial q partial x minus partial p partial y. What do we got? We've got partial x of partial h partial y minus partial y of partial h partial x. All right? But up to the level of being careful about analysis in this course, I mean, okay, technically speaking, you have to have that h is twice continuously differential. I mean, there's a condition which has to be met for partial derivatives to commute, but let's suppose that that condition is met. Of course, we know partial derivatives commute, yeah? So this is 0, which means that this exact form is necessarily closed, all right? The other direction, it's not always true. It is not generally the case. The other way around, closed on U does not generally imply exact on U. All right? There are counterexamples. All right? I'll show you one here, hopefully. However, if we add a topological condition to U, it turns out that that implication is in fact realized. However, if we insist U is simply connected, all right, then closed on U implies exact on U. Now, before I prove that, we should stop and appreciate what exactness of a differential form means. All right? What does the exactness of H mean? What are other equivalent characterizations of exactness of H? What does that mean in terms of vector field language? Yeah? Equivalent concepts to exactness of omega equals to pdx plus q dy equals to dh on U. So what I wrote at the top of the board here was our definition. Yeah? No. We're not. We have not yet written down the complex line integral. We have not meaningfully. We have yet to meaning. We have. Okay. Here's the difference between what we're going to do and what we're currently doing. What we're currently doing is additive. It's completely additive. At no point have we used the complex multiplication in anything we've done. Not really. All we've done is written real plus I times imaginary and applied the real theorem to separate pieces and said, voila. What you're talking about, complex differentiability, has to do with the derivative being multiplication by a complex number, essentially, right? That's a multiplicative feature, and that's the kind of thing we're going to pick up results about that once we talk about the complex line integral. We have not yet done that. We'll soon. We'll soon. All right. Okay, so this is more boring than that. So there's a theorem, FTC, and it says that the integral of dh, yeah, over a curve that goes from, say, p, oh, p's a bad choice, I don't know, Pac-Man 1 to Pac-Man 2, so this is the curve C, all right, integrate over that curve with terminal points Pac-Man 1 and Pac-Man 2, yeah? Then the integral of dh is h of Pac-Man 2 minus h of Pac-Man 1. This is the fundamental theorem of calculus. And the proof of this, again, I won't even write down. It literally follows from applying the regular fundamental theorem of calculus for line integrals separately to the real and imaginary parts of h. Look, let me demystify it a little bit. If h is equal to h1 plus ih2, if that's the component breakdown, then in our current notation, dh is literally dh1 plus I times dh2. That's the breakdown. And those, dh1 and dh2, are just plain old garden variety differentials of real valued functions, right? So a proof, I'm about to write down fine, I'll write down a proof. Make this a homework for the next mission. What did you say? Why would you say that? Is that what would you? It's Pac-Man 1 to Pac-Man 2, yeah? If you're willing to use this as a notation for the integration that goes from one to the other of dh, it's equal to the integral over Pac-Man 1 to Pac-Man 2 of dh1 plus I times the integral over the Pac-Mans of dh2. And those, I can separately apply the ordinary calculus 3 fundamental theorem of calculus for line integrals. Yeah? So these are exactly h1, of Pac-Man 2 minus h1 of Pac-Man 1 plus I times the difference of h2 at the Pac-Mans. And so rearranging it, that's h1 plus ih2 evaluated at Pac-Man 2 minus h1 plus ih2 evaluated at Pac-Man 1, which of course is precisely what we were trying to show. To say a little bit more though, okay, so let me just say a little bit more here. We're talking about p dx plus q dy, yeah, is omega. So if you look at that, it's a p1 dx plus q1 dy plus I times q p1 p2 dx, yeah, plus q2 dy. I think if I did that right. In the case that these are debating. If this was a test, I would be out there already. But I know you go get the free food. Yeah. All right. So this, if this is equal to dh, right? If this is exact, then this is the dh1 and this is the dh2. What's that mean? That means that the gradient of H2 is P2 comma Q2, right, in the usual notation. The gradient of H1 is P1 comma Q1. If you're willing to extend the definition of gradient to complex valued functions, right, if you're willing to talk about the gradient of H, right, if you want to talk about things like complex 2 vectors, you could do this. I don't usually do that, but if you did, that would probably be what that should mean. But I'm kind of not wanting to write this. I mean, back off of that. My point to you is simply this, that the real component, like the real components taken together, the imaginary components taken together, give you separately a pair of what? Conservative vector fields, right? What do you guys know about conservative vector fields? What are other equivalent characterizations of conservative vector fields? What are the equivalent characterization of conservative vector fields? So, number one, you know, that the vector field is equal to the gradient of some potential function in our current notation, h perhaps, yeah? I usually use a little, we usually use a little f, right? So that there exists a potential function that it's equal to the gradient of, right? So in our current notation, that is being picked up by the fact that pdx plus qdy is equal to dh. I mean, that's the equivalent version to that. In other words, I'm saying that saying a one form is exact is an analog of saying that the vector field f is conservative. Because it's essentially saying we can build the pdx plus qdy as a gradient. All right, I gotta stop. Hey guys, could it comes in here? Could we? Yeah, sorry. Thanks. All right, 2. Probably doesn't bother you. It's just like that kind of talking, it disturbs my thinking. And my thinking is disturbed enough already. So, all right. So path independence, yes. Path independence. So we have, you know, this, right? Well, let me not write down that. Let me just say words. Path independence. You know what that means? Yeah. We have path independence. In other words, if we integrate the vector field along one path or another path, and they share the same initial and terminal points, we get the same value, right? That is equivalent to this. And 3, the integral around a loop is what? Is 0, yeah? Integrals around loops are 0. And what was the 4th condition? The 4th condition is actually the closed condition. It's that the curl of f equals to 0. But that, in 2 dimensions, doesn't look like curl. It looks like, you know, partial q, partial x equals to partial p, partial y on simply connected u. You still need the simply connected for the 4th condition to be equivalent. All right. So we talked about the interrelation between these things, and the path independence. Actually, what's one of the very interesting things is the proof that path independence implies that there's the existence of f. Like to go from here to here, the proof of going from 2 to 1 actually motivates the typical definition for potential energy that we use in physics. So the formula is something like this. Path independence says we can build little f of a point r is equal to the integral from some reference point r naught to r of f dot dr. I mean, this defines the potential energy. Well, you got to put a minus in, but with add a minus in there, that defines the potential energy function due to the force F, assuming, of course, that the force is path independent. That's how you build the potential energy. Okay. So we have this different ways of looking at conservative vector fields, and consequently, different ways of looking at exact forms, right? Because they're the same thing. So if we have an exact form, that means it should be what? Independent of path. It should integrate around loops to 0. Yeah? So let's use that to prove that simply connected and closed implies exact. How do we get it? So we're going to assume U is simply connected. All right? And we'll let R be some region inside U. Okay? R is like a rectangle inside U. We can do that since it's simply connected. And what else? We also want the form P dx plus Q dy to be what? We want it to be closed, yeah? I'd like to show it's exact, right? So I can pick at exactness any which way I want to from calculus 3. I can either show integral around an arbitrary loop in zeros, loop in U is 0. I could show that it's got path independence. I could show that there exists a gradient. I mean, there exists a potential function, right? Like directly, I could show exactness. I mean, I got choices. But the most convenient choice is to show that the integral around a loop is 0. And the reason for that is we have Green's theorem, right? So consider the integral around the loop, which I'll call partial r, because the point is we can take a loop inside U and we can shade it in. That will give us a simply connected region that's inside U. Because U is simply connected, we can shade in any loop inside U and get a region inside U. That's part of being simply connected. And so I can apply Green's theorem to that simply connected subregion of U. Yeah? And so Green's theorem on P dx plus Q dy, what's it give me? It says that that's the integral over the area, R, of partial Q, partial X minus partial P partial Y. And lo and behold, that's identically 0 because that is the closed condition. That vanishing is the closed condition. And so we get 0, right? But, you know, boundary of R is arbitrary loop. Arbitrary loop in U, which implies, you know, that it implies path independence. However you want to look at the equivalence. Anyway, so we've met condition 3 of our list of equivalent conditions for conservative vector fields, right? And each component, if you will, of DH it corresponds to a conservative vector field. So this list is duplicated for the real and the imaginary part, yeah? Thinking through it. So basically, then this implies that we've showed the integral in a loop is 0, therefore omega is equal to DH on U, which is to say it's exact. All right? This discussion is probably worth having in here because, in part, this material tends to get shortchanged in Calculus 3, or it gets a full treatment in Calculus 3, and it gets fully forgotten by Calculus 3 students. That's probably more often the case. It's like, I'm studying for the final, I've almost got an A, everything else really makes sense. This one pesky little corner of the course is scary, and I've got other things to do. I'm not going to settle every single issue that is attached with vector fields in their calculus, right? I think that's a pretty typical student attitude here at the end of Calculus 3, from what I remember grading Calculus 3 finals. But anyway, getting to a point here, guys. All right. So I actually, in my notes, so in the notes from Chapter 8, I actually work out a lot of the details of this equivalence, all right? And it's essentially just Calculus 3 redone here, all right? Just for complex valued things, so I don't want to belabor it at the moment. What I do want to show you, though, so we have had this, one of the things we have enough technology to do at the moment is talk about harmonic conjugates, yeah? And this actually will have some relevance to your test, because I might ask you to find the harmonic conjugate for a given function, right? And you had two choices, right? Which one? What were the two choices? Either just like through your own like willpower, vision, creative genius, whatever you want to call it, go, aha! That's the real part of such and so forth complex function. Done, right? Which is fantastic when it happens. Or you do what? You integrate the Cauchy-Riemann equations to find your way from U to V, right? So it would be nice to have an existence theorem that knows that that search is not vain, yeah? And that's what we have here. So this is my lemma, section 8.3 on harmonic conjugates. I'll start with a lemma, which is that if U is harmonic, all right, then the differential minus, so this is a little bit weird, minus partial U, partial Y, dx, plus partial U, partial X, dy is closed. This is almost a kind of silly lemma in some sense, right? Because the proof is what? What does it mean for U to be harmonic? We have what? Uxx plus Uyy equals to 0, right? And so this is my P, this is my Q. I need what? The closed condition? I need Qx minus Py, which is what? It's minus Uy x. Wait a minute. Oh, I'm an idiot. What, can I just follow my own definitions? I said Q is partial U, partial X. What did I put down here? Minus partial Y, because I'm an idiot. That was plus Ux, yeah? And then minus, parentheses, minus Uy, partial derivative of that. By the way, guys, isn't the sub-letter partial differentiation notation amazing? We should pause to appreciate this notation. And the amount of writing it just saved me. Okay, thank you. Uxx plus C. If they were talking in the hall, I would not have made that excellent comment just now. All right. So the point is, closed condition, closed, right? Yeah? Okay. So that's the proof is done. Theorem. If U is harmonic on a star-shaped domain, all right, then there exists V of xy, V on, and let's call the star domain D. There exists V on D such that F equals to U plus IV is holomorphic on D, which is to say what? In other words, what I'm saying is that V is the what? The harmonic conjugate, right? I'm saying that there exists a harmonic conjugate. If you have a harmonic function on a star-shaped domain, we can prove there exists a harmonic conjugate. What's star-shaped? You guys have homework, right? Yeah, we talked about that. So how's the proof of this go? Oh, it's actually kind of interesting. So the proof actually follows. I was kind of expecting another, we commute partial derivatives, things go to 0, yay, we're done proof. No, it's not that. It actually involves the proof of the red arrow. It's that kind of proof, because what you want to do essentially is, I don't know how to say it even. Well, I'm not sure we have time. Yeah. It says basically construct the potential function for minus partial u, partial y, dx, plus partial u, partial x dy. Now, why can we do that? Let me call this thing omega. We have that omega, omega is a closed form, right, by the lemma. If we have star-shaped, is star-shape implied simply connected? It does, yeah, it does. Star-shaped is a lazy man's simply connected. Like simply connected is a more esoteric and many-faceted, curvy monstrosity. Star-shaped is nice, simple, easy to think about. So yeah, star-shaped does imply simply connected, which means that we have a closed form on a simply connected region, which means by our previous discussion, we have a exact form, right? So thus, as D is simply connected, because star-shaped implies simply connected, that implies that omega is exact. And so, thus, omega is equal to dh for some h on D. And the way you construct h, all right, h of z, you just define to be the integral from z naught to z of the omega. And so in this context, it would be minus partial u partial y dx plus partial u partial x dy, I believe. This gives us the formula for h of z. And I think, in fact, that h of z is what? I should really say, I should really just say, let me change these h's to a v, get to the point of it, because this h is the v we're looking for. So here the picture, something like here's z naught, here's z. You know, we can connect from z naught to z. Z naught some reference point in z, and that will give us a harmonic function. Okay, so just let's see here. How can we prove this is a harmonic function? What does it need to satisfy? Yeah, certainly if we could show it if we could show it satisfies Cauchy-Riemann equations, right? And it was continuously differentiable. So assuming that u is continuously differentiable, all right? Assuming u is a nice function, and that is something we're assuming here. That means that these coefficient functions are nice, right? And so you're integrating nice things, you're building something nice is the bottom line, okay? So, and then the question is, what is partial v? What is partial v, partial x? What's partial v, partial y for this formula? If you study the proof of the red arrow, that proof essentially walks you through the fact that when you partial differentiate an integral with a variable bound, just what you expect happens. In particular, we would get partial v, partial x equals to what? And partial v, partial y equals to what? Care to guess? Ooh, it's unusual. So v partial x should give us minus uy, yeah? And in fact, v partial y gives us partial u partial x, which of course are the Cauchy-Riemann equations, hence v is harmonic, if it's so constructed. If you look at what this is just what you've already been doing, though. This is nothing new. See, because this is what? I mean, this is we're setting this equal to Vx, essentially, right? And we're setting this equal to what? Vy, essentially. The things that are above what I just wrote in red are given to you if you're given u. So you take the u, you partial differentiate it, and then you integrate with respect to x, and you integrate with respect to y, and you put those things together. That gives you the harmonic conjugate. This is already what you did. It's just that this is a proof that it can be done in general. Yeah. Well, star-shaped domain. So, all right, so we have 2 minutes left, just enough time for me to get in trouble. Uh-oh. Yes, Sam.
Do we need star-shaped, or do we just need
I think simply connected will do. Yep. So I have still not defined the complex integral. I will do that now. If f equals to u plus iv is a function from, some subset of the complexes to the complexes, and C is curve, parametrized by, let's say, gamma, which goes from, say, T0, T1 to C, all right? Then the integral of C of f dz is equal to the integral of f of gamma of t times d gamma dt from T0 to T1. This is definition 1. Definition 2. Definition 2 you might like, or you might not, I don't know. Pick your poison here. The integral over gamma, over C rather. I used gamma for my curve here, but integral over C of f of z dz, check this out. It's the limit as n goes to infinity of the sum j equals 1 to n, yeah, of f of zj times zj minus zj minus 1. Let me explain what I mean by that. Here's my curve C, yeah? And so we've got, Z1, Z2, Z3, Z4, Zn. Yeah. So you're like, there is a third way of defining the integral. Sorry I got started late today. It was actually not my fault this time. The third way of defining the integral, and then we'll call it a day. The third way of defining the integral would be this. And you're going to like this, I think. I mean, I like this. It's fascinating. It works like this. So it's, if you think about dz as literally being dx plus I dy, another way you could define the complex integral is in terms of the integrals I've already written today. And you could just say, you know what it is? It's u dx minus v dy. See that complex multiplications into play, Sam? I just multiplied I. That's the difference between what we were doing and what we're currently doing. U dy plus v dx. And so these are three, in fact, equivalent but competing definitions for the complex integral. We could look at the complex integral any which way we'd like here, and these are, in fact, interchangeable definitions. But we do need to assume that the curve we're integrating over is appropriately. It can't be too bad a curve. I mean, the curve has to allow this setup, yeah? Any questions? So I will explain more about this next time. Yep.